All right, lights on, we're recording. All right. I just don't like saying anything and then people at home missing out, especially on a Wednesday morning at 9. Seems like there's a few people who've stayed home this morning. The traffic was terrible too, so. All right. So this is the first announcement that David has made for the class test. I mentioned it also on in Monday's lecture. So just a reminder, I'll probably do another one tomorrow morning as well, just to make sure that everyone knows, because there's always a few emails at the end going, I didn't know there was a class test on. But also all the important announcements will be through the announcements portal here. So you'll see them all here, and you'll see that I've read all of them, obviously. But also, previous semesters, I've made a mock class test. So that's not worth anything, but it gives you a good indication of what to expect for next week's class test. So you can go there and have a look. So there'll be multiple choice questions for David's component, and then for this week, for me, for the component I've taught this week. And it's good because after next week, you'll also have done the tutorial, so it should be all good. And then also has 2 long answer questions, one for David and then one for me. And there'll be another one after thermal physics, and then another one after electricity and waves and oscillations. So yeah, but that's the only mock class test, just so you know how to submit PDFs and whatnot onto Canvas. I think that's it. Was there any questions before we move on about the class test? No? All right, make sure it's all working. Nice big screen in here. So we did a very basic lecture on Monday. We'll just look at standard units, base quantities, and then also vectors. So we're going to move on and actually apply those things, in particular vectors, and we're going to look at motion in one dimension today and kinematics. So we start this week looking at kinematics, and that's basically things that change over time. Next week we'll look at dynamics, where we're pushing things with a force and Newton's laws. So that's what we'll cover today. So we're going to define some different words that you've probably heard of before, but it's such a broad distribution of knowledge in this class, so we have to cover all our bases. So we've got things like displacement and how that differs to distance, average velocity, but then also instantaneous velocity, and then also the acceleration derivatives as well, so average acceleration and instantaneous acceleration. And then we're going to look at how we can solve problems. So in today's lecture, we're going to look in the X direction, or going horizontally, and then in the Y direction, going up. And so I want you to start thinking about what different accelerations might occur, especially with the up one, and we can apply the different kinematic equations that we'll see today. And then in tomorrow's lecture, we'll combine those with projectile motion. So it should go quite nicely. So kinematics is the study of motion. So basically we're looking at how something moves as a function of time. And so we've got velocity, or the speed that it travels at, and we've also got acceleration. And so you can think of a runner, especially with the Commonwealth Games at the moment. You can think about how that runner may have variations with the velocity and acceleration, and how you may look at the average velocity and average acceleration throughout a race. And that will change depending on what type of race that is. So I made lots of little animations, so let's hope the audio works today, and we'll start with instantaneous velocity and speed and defining those terms. Yep, very quiet.
Imagine that a student, let's call them Sam, is casually walking to university to attend a lecture. They are walking at a speed of 1 metres per second. Sam receives a text, and to their delight, there is a free sausage sizzle at Shortland with vegan options. The only catch is, they usually run out at 12:30, so Sam did what any poor student would do, and begins running. Sam starts sprinting at 6 metres per second, but realises they're not as fit as they used to be, and that textbook is a beast. Sam slows down to 3 metres per second. They receive another text from their friend. They have saved a spot in the sausage sizzle line, but Sam has to be quick. Boom! Sam makes it. Okay, so let's look at how Sam travelled. These values here are Sam's instantaneous speeds, which is the speed of an object at a particular point of time. If you include the direction, you get a vector with both magnitude and direction, which is the instantaneous velocity. To find the instantaneous velocity, you would get a smaller displacement and time interval. But to do this, you need to find the average velocity over a really small time period. This is different to the average velocity given the distance travelled. For example, if the student ran 2 kilometres or 2,000 metres and it took a total of 10 minutes, the average velocity would be 2,000 metres, divided by the 600 seconds it took. The average velocity would be 3.3 metres per second, which doesn't necessarily equal the instantaneous velocity at any one point. This is the same for acceleration. Average acceleration is the change of velocity divided by the time taken to make the change. Instantaneous acceleration is the average acceleration over a really small time period.
All right, so what we sort of covered in that little animation is just some different definitions. So, and these are what we're going to cover for half of this lecture at least. So we have displacement. So that's defined as a change in position of an object or runner or whatever it is. But this one has both magnitude and direction. So you'll have to have the direction included in that, and it's a vector quantity. The distance travelled, however, will be just the total length of the path taken, and it only has magnitude. And we'll see how we can see one of our other physicists who bike rides, see her little pathway to uni and how we can compare those two in a moment. We have the average speed, so that's the total distance travelled. So again, that's this term here, distance travelled divided by the time taken. It only has magnitude. And then we have the average velocity, which is a vector quantity, so that's where we have the displacement divided by the time taken, and it has both magnitude and direction. And so that will just give you an average over the travelled period of time. Whereas instantaneous velocity, that's where we will look at an infinitesimally small time period, and we'll divide the distance travelled divided by that time, and we'll get the instantaneous speed. And if it has direction, we change the word speed to velocity to get that vector. So to look at how we calculate it, we've got these equations here, which I showed briefly in the movie. So we tend to just simplify things in physics. We simplify the runner or the car to a particle, and that way we can just make it simple and have some sort of assumptions associated. So we have the particle moving along the x-axis. So like I mentioned, we're just going to go horizontally first, and we can find the change in the particle's coordinate using that delta x. So x meaning it's in the x plane or the x-axis, and this delta just means the change of again. So remembering that with that delta, it's the final position minus the initial position. So if you have those, you may have it in a vector form like we saw yesterday, and you can put those quite nicely into that equation. And then we get the average x velocity, and we just write that with v, AV meaning average, and then we've got the x-axis here. So usually when we have a specific coordinate we're looking in, we will just note it there so we don't get confused. And so it becomes delta x divided by delta t. So again, we can just substitute this part of delta x into the equation, and usually we can find the time period, and so we can put the delta t in there as well. It usually has an initial time of 0, so usually it's just the time taken. So you can divide that and get the velocity. And as it's written in the textbook, very similar. So we have the final coordinate being x2. So sometimes you'll see x1 as xi, meaning initial. Sometimes you'll see x2 as xf, meaning x final, or the final position. So both of those terms you'll see. And then we've got the t, so initial time and the final time, and we can find the average velocity for that application. So we can have a look at this, again, a swimmer, because it's lots of racing going on TV. So we have a winner of a 50-metre swimming race. And the swimmer's average velocity has the greatest magnitude. So that's how we can find out who's going to win. So the swimmer who transverses across the x-axis with a displacement of delta x of 50 metres in the shortest elapsed times is the winner. And so you can sort of look at how that average velocity is used for that particular application. And we can even draw a graph, and we're going to see a few graphs because that also comes in handy. Again, there's all different ways that people like to learn these, and so we cover all of them. So we have the x-axis, or the displacement here. So we've got go up to 400 metres, and across the x-axis, I hope I said y-axis is x for displacement, and then the x-axis is t. And so we've got 5 seconds here, and so we can find that we've got 2 different points, and we can extrapolate the numbers there for delta x and delta t, just from the graph here. So delta t being t2 is 3 seconds, t1 is 1 second, and then again we can extrapolate across to the x2 position and the x1. So now let's look at how that changes with instantaneous velocity. So the instantaneous velocity is at a specific instant of time. So we just try and decrease this to as close as 0 to possible. And so what that looks like graphically is that we take the tangent of the slope, or the slope of the tangent. So this is what equals the instantaneous velocity. And that's why it's good to look at the graph as well as the equation. So some people will like either. So the average speed is not the magnitude of the average velocity, and that's really important to remember. So we'll look at how we can find that as well. And so most of the time you will be given an instantaneous velocity as well, but this is how you would find it as well. You'd take the derivative as a function of time, so the derivative of x as a function of time. And we'll have a look at how we can do that mathematically soon. So yeah, so we've got average velocity, instantaneous velocity, distance and displacement. So let's have a look at how that changes for a bike ride. So we have this map from Adamstown and to Birmingham Gardens. All right, so we've got the GPS unit coordinates, and you can typically get that with most of the different technologies that you can wear while you ride or run. So you can find the instantaneous velocity at any particular point, for example, 24 kilometres per hour. If we convert that to metres per second, it's 6.7. And then we've got direction as well. So that's important. We have our vector quantity there for velocity at a particular time point. But again, we've got the distance travelled. So that's going to be 27,500 metres. And that follows the red line. Whereas the displacement is just going to be the x2 position minus the x1 position, and we get 3.6 kilometres. So that's just a difference here from start to finish. So it's actually a lot smaller than the actual distance travelled. And then we have the time elapsed. We've got that on the data as collected as well. So it becomes 4,714 seconds. And so we can start to calculate the average velocity and speed. So the speed is one with no direction. And so that's just going to be the distance travelled divided by the time elapsed. And again, the average velocity is going to be the displacement divided by the time elapsed. So that's the two differences there. Okay, so obviously my slides haven't updated. So that's from, you can find those multiple choice questions on Canvas now. And we'll come back to that at the end of the slide, at end of the lecture. So we've got another example here. So we have just the x coordinate, we're not looking at y yet. So if we have a look at delta x, so we have a final position of 30 metres minus the initial position of 10 metres. And so for that we get 20 metres, and we can find the velocity knowing that it took 10 seconds. So that's no surprise now, that's been pretty drummed in. But then if you have a look at the direction as well, we need to make sure that we've got those signs correct. So for this one, the final position is 10 metres, the initial position is 30, so we get minus 20 metres. And so with that, we get our direction in the reverse. So we have a reverse vector for that example. But if we have something that moves from x1 up to 40, then back to x2 to 20, then we still only get a 10 metre displacement. And so with that, we get the velocity of 10 divided by 10, and that's 1 metres per second. And so we get the distance travelled, again, yep, that goes all the way up to 40, then back down to 20 is 50 metres, but the displacement is only 10. So these are the important factors to remember, and you'll get, we'll show examples this week and next week. So we're going to move on now because I've shown a few graphs where we've looked at displacement on the y-axis and then the time, and so that's what our derivative represents, right? The function of x, the change in x as a function of time. And so we can use this, and it's good because it's a segue into acceleration. So we have our x on the y and our t, and so what we can look at each point is the slope. So for point A here, the slope is positive, so we're going to have a positive velocity there because it's x versus time. It's the same as the equation. For B, it's also positive. It's probably a bit more positive, but when it's also when it's a slope of 0, so it's horizontal, then we have no velocity. So you should be able to look at a graph and pinpoint a position and sort of guesstimate what type of velocity you've got. Because if we have a negative one, we're going to have a negative velocity. So those are the things that you should be able to get from this graph. And similar when we look at V or velocity time curves as well. So if we find the derivative of velocity as a function of time, we'll find the acceleration, and I'll show that in a moment. So acceleration is the rate of change of velocity. So velocity being the rate of change of displacement, this one being the rate of change of velocity as a function of time. And so we have metres per second for velocity, we have seconds on the bottom, so our units are going to become metres per second. And I'll point that out because we learnt that Monday. So we can find the average velocity in the x-axis, shown here, as the change in velocity divided by the change in time. And we can write that in full using the v2x minus the v1x divided by t1 minus t2. So there's no surprise there. It's going to be pretty obvious from here, and so I won't explain as much as what I have been. So to find the instantaneous acceleration, it's very, very similar. We find the acceleration at an instant of time where we try and approach 0 or t equals 0 to find it. So we find the function, the derivative of velocity as a function of time, and we can find the instantaneous acceleration. So let's have a look at an example where we just have constant acceleration. But before I move on, is there any example where you can think of where we have constant acceleration? That might be obvious. You might have learnt it in high school already. Yeah, that's the one. So that's the next part we're going to look at is the y direction, where we have constant acceleration of gravity. So we're going to look at in the x direction because we're still doing that, but this is good to remember for the coming slides. So when we have motion with constant acceleration, the magnitude of acceleration never changes for that example. So we might start with initial velocity of almost 0, but you'll see that the magnitude of that velocity with constant acceleration will increase, as you would expect. And so when we look at this in a graph as an acceleration time curve, we will have a slope which is equal to 0 here, and so we have constant acceleration, and we have the area under the AT graph, which is equal to the V minus V naught, so the initial velocity is also represented with the O there, and we'll see that with kinematic equations. So it's important to remember how this influences the other variables, such as velocity and such as displacement. So you should be able to have a look at an acceleration time curve, go back to the velocity time curve, and then the distance time curve, and vice versa, and sort of estimate what's going to happen. So with acceleration, it's important to remember that it's not always deceleration as we think it is, like when we're putting a brake on or something. It's not always the case. So when we think about acceleration, it's not always meaning getting faster. So we use it for speeding up, slowing down, or change in direction with no change in speed. And that's another example that we're going to come across in later weeks. So you need to make sure you don't use deceleration as an acceleration when you should be using acceleration. So we have this example where a car starts at t equals 0 and has a velocity, v1, of minus 15. And it might slow down to -5 metres per second over a time period of 5 seconds. So here we still have a positive acceleration. It's not deceleration, we still get a positive 2 metres per second acceleration. So I've sort of implied this as we've gone, but there is integral relations. So we should be able to go displace, if we know the time, we should be able to find acceleration, the velocity and acceleration. And then we can actually go the reverse direction as well, if by applying derivatives going to acceleration and then the opposite integrals going back to velocity. So we can find that. So with the velocity derivative for the x, or the change in displacement as a function of time, and we can also get the displacement by finding the integral of v. Similar for acceleration and velocity. And again, we can see this in the AT curve, the VT curve, and the XT curve. So this is the acceleration, velocity, hopefully you can see that all right, yep, and the acceleration curve there. So again, I've got these slides. I did change it, but sometimes it doesn't update. So we're going to move on to instantaneous velocity and speed, and we're just going to reinforce what we've learnt, and then we're going to move on to different examples, and I'll show you some solutions to how we can solve them.
Velocity time graphs can be a very useful tool for physics and is often overlooked. They can help to calculate distance travelled when given information about velocity and/or acceleration. Here we can draw the displacement, velocity and acceleration versus time graphs for an object. If you have acceleration or velocity, you can integrate to find either velocity from acceleration or displacement by integrating velocity. Let's draw the first 4 seconds of each graph. The displacement initially has an increasing slope. This means that the velocity must increase, which is illustrated by the positive slope here. The positive slope for velocity means that not only is the acceleration constant, but it is also positive. From 4 to 7 seconds, the displacement has a constant slope, which means the velocity must be constant. If there is a zero slope for velocity over time, there is zero acceleration. Let's look at displacement over 23 seconds. Initially, there is a decreasing slope. This means that we get a decrease in velocity and a negative acceleration. You will also notice that at the highest displacement point, there is a zero slope, which corresponds with an intersection here for zero velocity. The negative slope for displacement beyond 15 seconds means that there is a negative velocity, and a negative velocity slope implies there is a negative acceleration. As the slope flattens, the velocity becomes less negative and you get a positive acceleration. When the object has a zero slope for displacement over time, this implies the object is at rest and both the velocity and acceleration over this time is also zero.
All right, so we're going to move on to an example now. Actually, I should probably show you the example first, which is going to be, because I didn't get a chance to put it on here, so let's go back. All right, so here's an example. So I've got a displacement time curve here, and so we've got a graph that's showing the xt expression that we have here, so 10 minus 5t plus t cubed. So we're going to apply what we just learned about the integral relations and also the derivatives, and we're going to find the instantaneous velocity and acceleration at 2 seconds, and then we're going to find the average velocity between 2 and 6 seconds and the average acceleration between 2 and 6 seconds. So that's what we're going to have a look at now. So how would we use that equation to find the instantaneous velocity and acceleration at 2 seconds? Does anyone want to have a go? Maybe just start with the velocity first. So easy, yep, that's good. So we are present, which is great. All right, so we're going to take the derivative of that. So let's write that equation down. Let's hope it works all right. Okay, so zoom in. One day the internet's firewall will let me do live screen shares, but up until then I have to make do with this. All right, so this is our displacement equation that we have. and so we can find the derivative of that. So remembering that our Vt is equal to dx over dt, or the change in x over the change in time. So we can simply plug in that expression into x. So to do that, we can find 10 minus 5t plus t cubed over dt. And so what we'll get from that derivative is we won't get the 10 propagating down, we'll get minus 5 plus 3t squared. So if you can't remember how to do the little derivatives, there's some maths help on Canvas. Also, you can come and see me and I can give you a little overview. But yeah, so this one is a constant, so that's not applied. This is to the power of 1, so it's simply 5 or minus 5 times 1, and then the t is removed because it's a 1 minus 1, 3 minus 2, and we get the 3 out the front. So we get our expression for velocity, and we can simply plug in the value of time at any particular point. So we're going to do the same for acceleration. Make sure I've got that up so you can see it. All right, so dv over d time, and we can plug in our velocity term now. Like so, and we can find the integral for that, and that's just going to be 6t. So that's our acceleration term. Try and write it a bit neater. All right, and I'm going to put the units just to be consistent. All right, so once we've got that, we can actually find the instantaneous velocity. So that was at 2 seconds. So we can put in 2 here and here, and then we can put 2 in here, and we can find the velocity and acceleration. So I'm not going to do that because we've got to do it again anyway for part B, and that's a pretty simple part that you could probably do at home. So we're going to move on to part B. What is the average velocity between 2 and 6 seconds? So we're going to write the equation for average velocity just as a reminder. So it's delta x delta t divided by delta t, or we could write that in full. X2 minus x1. Make sure you can see that all right. Sorry, guys. X2, T1, T2 minus T1, and then we can find X2 position, and we can find the X1 position, and we can plug those values in. So for X1, where X, right, wrong. So where X, we're finding X at 2 seconds. We can have 10 minus 5, and then we'll have 2 plus 2 to the power to the power of 3, and so we should get 8 meters. Similar, we can find x2, and so that's going to be at 6 seconds. Reminding myself, 10 minus 5, 6 to the power cubed, and then so we should get quite a large number for that one, 196. And so we can plug those into our expression. So we have x1, x2, and we have our time as 6 and 2. So again, you can plug those in, and you should get 47 meters per second. So that's the constant velocity. So what I'm going to do is I'll let you do the constant acceleration at home, and it's also on the slides as well. So it's similar, you're just going to change this equation to average acceleration. All right. So we had a question earlier and someone got it right, a special case of acceleration. So we can have a look at the equations and we can find kinematic equations where we have constant acceleration. So this is where we can actually apply some of the stuff we've learnt and find some equations that we can use to solve things moving in motion, either horizontally, vertically, and then in tomorrow's lecture in a parabola. I'll be able to say that word. All right, so we can find the integral for velocity to find an expression for x. And so what we can do once we find, I've got this one here, v equals v naught, so that's that initial velocity. I think in high school you use u. Is it in New South Wales, is it? I didn't actually do high school here, so yep. So we're changing that now in physics in tertiary to v naught. And there's probably going to be some other variations. So we can put this equation that we've got here from finding the velocity integral of acceleration, and we can put that into our equation, and what we get is this v naught, the initial velocity, multiplied by time plus a half at squared plus c, which is a constant. Now, you don't have to remember how to derive these. What I want you to know how to use is the ones in blue, the equations in blue. They'll also be on all the equations will be on an equation list anyway, so you don't have to remember them, you just need to know how to use them. All right, so we've got at t equals naught and x equals x naught, so that's at the initial time of n0, we have an initial position of x naught. So we can put that as our c2 constant here, and we get this expression for displacement. And then we could also find the average velocity expression, and we get this derivation for v squared. And again, you can see the textbook for that. Again, we're not going to go through it. You don't need to know it. I'm not going to ask you in an exam how to derive these, but it's good to know how they came about. So we've got some familiar kinematic equations for constant acceleration, and we're going to have a look at those now. So this will be towards the end of this lecture. We're going to look at vertical motion, and then we'll be ending it.
Imagine an object thrown straight up in the air. Is it accelerating the same? Yes, the object thrown upwards and downwards will experience the same acceleration as the object released from rest. Once in free fall, all objects will have constant acceleration downwards. And acceleration is equal to the acceleration due to gravity. Now that we know the acceleration is constant, let's rewrite the kinematic equations that we have already learnt, remembering our special case for constant acceleration. We can find the velocity at a given time point knowing the acceleration and initial velocity, which is sometimes zero and can be simplified further. The first equation we see is velocity equals the initial velocity, v naught, minus g, the gravitational acceleration, times the t for time. We know there is no displacement in the x direction, so this doesn't play a role in our equations. You can find the displacement in the y direction if you know the initial position, initial velocity, and the time taken. Again, this can be simplified if the initial position and velocity are zero. So let's look at this equation. So the y displacement is going to be equal to the initial y displacement, y naught, plus v naught, the initial velocity, times t, the time, minus a half g, which is the gravitational acceleration, times t squared for time again. If you come across a problem where you don't know the time, the next two equations are useful. One to determine the velocity, which is v squared, or velocity squared, equals v naught squared, minus 2g for the gravitational acceleration, and in brackets, the difference in the y direction, so y minus y naught. And another one, to calculate the average velocity, can be the average velocity is equal to the velocity plus the initial velocity over 2.
So I always find that the equations are quite easy to use, but sometimes hard to apply in a problem. So the best advice I can give is to write down all the variables that you're given within a particular problem, and then try and figure out what you need to find. And usually it follows similar strategies where you need to find the initial velocity and then the time. So it's just making sure that you get used to that sort of problem solving. All right, so we're going to look at free-falling objects like the previous animation. So when we're looking at free fall, the motion of the object is only influenced or accelerated by gravity. So there's a multiple choice question that's coming up in the test your knowledge one if you want to do it, and it asks if you throw a ball straight up, what's the acceleration? It's constant, but what about if you throw it straight down vertically? as hard as you can. Will that change the acceleration? No. All right, so good. So that's what we want to drum in. So the velocity change is going to be the same in each time interval. So if we have a look at the strobe ball, we have it changing the displacement only slightly, and then that displacement will slightly increase with every interval. So it's the same time period taken for each of these photos, but it's going to increase. And this is a summary of the different equations like I showed in the animation. So we have the velocity equation where we need the initial velocity, so sometimes that's where you need to find the initial velocity, minus gt, and we have y, so because we're only looking in the y direction. So when we start looking tomorrow at the projectile motion, these equations will change to the r vector, and we have velocity squared, and we can tend to use this to find the change in displacement. So yeah, they're the different ones that you'll probably need to remember for the y direction. And then again, I've got these in the wrong position, so we're going to move through. So we're going to have a look at this example, and this is the last example, and then that's the end of the lecture, so that's good timing, and then you can do the online multiple choice questions if you like. But let's have a look. So a stone is thrown vertically upward with a speed of 24 metres per second. How fast is it moving when it reaches a height of 13 metres? And how much time is required to reach that height? So they're the two questions that we're going to look at. And so the first thing I'll do, after I fix this up, is I'm going to draw an image. It's good to get used to this, especially when we start looking next week at Newton's motion. We will start to look at free body diagrams. So we have a ball, it's thrown up in the air, and we know that the height that we're looking at is 13 metres. I'm going to do the correct significant figures to make sure I do it properly. All right, and we've got a v naught, initial velocity, of 24 metres per second. So that's good, we already know that. And so let's have a look at the different equations that we can have. So we have v equals v naught plus at. Obviously, this is going to be negative because it's negative 9.8, but I'm not going to put that into the equation yet until I change it to g. All right, and we've got y equals y naught t plus a half at squared. And then we have the other equation for velocity squared, and this one's v naught squared, or the initial velocity, 2 times acceleration. There we go. And then we've got the change in y. All right, so there's our three equations. And what we know is v naught, so we'll list those off here. V naught is 24 metres per second. And I'm even going to put a little y there. Y is equal to 13.0 metres. What else do we know? Oh, besides also this one. Minus 9.8, that's an easy one. Is there anything else we know from that list? The difference in y is 13? Oh, 13. Yeah, yep, so we can say that y naught is 0. Yep, so that gets rid of this variable here. So basically we can cross that out because it's 0. But we don't know v, and we don't know the time. All right, so what we can do first off is we can find v, and then we can find t. So what we're going to do is use this equation here. So for this one we get v squared is equal to v naught squared plus 2a y minus y naught. And we have to get rid of the square here, so we can square root both sides. And we get that expression, and we can start putting in. So like you said, that's the change in y. It's going to be 13 metres per second. We have initial velocity of 24, so we can actually solve that solution quite easily. And we also have minus 9.8 here. So what you should get for that one is 179 metres per second. So we can now apply that into the next equation. So this one here. So v equals v naught plus at, and we can rearrange to get t. And so what you should get is 179 equals 24 plus, actually, minus 9.8 t. So you can rearrange that and you should get a pretty reasonable number of about 4 seconds. So I'll get you to do that more accurately. So that's pretty straightforward, isn't it? Yeah? So it will start to get a bit more confusing, I find, with students when they start to look at projectile motion or different examples. So the only advice I can give is to have a look at all the problems that we go through in lectures, tutorials, and the laboratory, but also the textbook. Have a look at the textbook and how they solve the problems as well. And yeah, so that is it for today's lecture. So what you can do is you can go onto Canvas and have a go at the multiple choice questions. You can come down and see me and have a chat. Tomorrow we're going to look at motion with vectors in both the X and Y direction collectively. All right, thank you. Put my mask on. Hey, how you going?
I have a question about the masters.
Yep.
So is that next week?
Yeah, so let's have a
So I
look.
saw on campus there was like a mock exam.
Oh yeah, I did mention that at the start. I think you must.
Yeah,
Did you
I
come in a
must
bit
have,
late?
mate.
Yeah,
Yeah,
that's all
that
right.
was my fault.
That's all, no, I'll say it again tomorrow anyway. But yeah, so the mock class test is here.
Yeah.
Yeah, so that's going to be really similar to the test next week.
Yeah,
So
gotcha.
it opens at 8, closes at midnight
Yeah,
on
right.
Friday.
Gotcha. No worries.
Yeah, so you can have a go at that. It's going to be really similar, and that way you can practice uploading.
Yeah, perfect.
Yeah.
Sweet. Are all our exams online for this?
I know that David's going to apply for a face-to-face exam.
Okay, gotcha.
Yeah, and they approved mine last semester, so it'll
Yeah.
probably be face-to-face.
All right, no worries.
Yeah.
Awesome. Thanks for
No,
staying.
no worries, thanks. Yeah, thanks.